Today we will discuss about the application of Fermi-Dirac statistics. We have learned earlier that Fermi-Dirac distribution function f epsilon equals to 1 by e to the power epsilon minus epsilon f by kBt plus 1, and we know that epsilon is less than equals to 1 and the number of particles in a state would be less than or equals to 1. For t equals to 0, we see that thus the distribution function behaves like a step function which ends at epsilon equals to epsilon f. For other temperature, the abrupt decrease or abrupt rise of the curve is not, then there is a slower decrease, and for t2 greater than t1, the curve is like that, where t2 is the farthest part. For t equals to 0, what we get? Epsilon is greater than epsilon f. So f epsilon equals to 1 by e to the power infinity, as epsilon is greater than epsilon, plus 1 equals to 0. And for t equals to 0, when epsilon is less than epsilon f, then we get f epsilon equals to 1 by e to the power minus infinity, as epsilon is less than epsilon f. So we get equals to 1. And two case, the distribution f epsilon equals to 0 or 1 for when that epsilon is greater than epsilon f or epsilon is less than epsilon f. For other temperature, that is t greater than 0 and epsilon equals to epsilon f, we can have the f epsilon equals to half. Thus at t equals to 0, all single particle state up to epsilon equals to epsilon f are completely filled with one particle in each state according to Pauli exclusion principle. All single particle state with epsilon greater than epsilon f are empty. So Fermi energy is the topmost occupied level at t equals to 0 Kelvin. Now total number of particle, we can get it by integration of number of particle lying between epsilon and epsilon d epsilon from 0 to infinity, and n epsilon d epsilon can be written as g epsilon f epsilon d epsilon, and where g epsilon is the density of state, which can be written as from the momentum space and configuration space. P is the integration of the configuration space, and momentum space integration g 4 pi p square by momentum sphere 4 pi p square dp by h cube, and the g is the multiplicity factor due to the spin state, due to the spin multiplicity, and g equals to 2 for electron. M is because it has two states, spin up and spin down, and we get gp g epsilon d epsilon equals to g 4 pi v by h cube 2m epsilon whole over half m d epsilon, where we use the p square equals to 2m epsilon. Now total number of particle n and total energy U can be written from the g epsilon d epsilon, and epsilon equals to, in the first, the difference between the first and second is epsilon to the power half, and here is epsilon to the 3 by 2, because here we use the n epsilon d epsilon, epsilon is multiplied. At t equals to 0, what we get? F epsilon equals to 1 for we got earlier. So n equals to, we can write this, the big function become equals to 1 or 0, and we get the 4 pi gv by 3h cube 2m to the power 3 by 2 epsilon f to the power 3 by 2. So epsilon f equals to 3n by 4 pi gv to the power 2/3 h square by 2m. N by v can be written as rho, so we can write the equation as 3 rho by 4 pi g to the power 2/3 h square by m, and Fermi temperature can be defined as Tf equals to epsilon f by k. The ground state energy, the energy at 0 Kelvin is U0 equals to 2 pi gv by h cube 2m to the power 3 by 2 0 to epsilon f, that is the total energy is up to epsilon f at 0 Kelvin. So integration is from 0 to infinity. Instead of 0 to infinity, we are using 0 to epsilon f, epsilon to the power 3 by 2 d epsilon, and the result comes out as this. So U0 by n, the number of the average energy per particle, energy by particle, is comes out as 3 by 5 of epsilon f. Ground state, equation of state for the gas at t equals to 0. pressure can be written as 2/3 of energy density. Then energy density U0 by V into 2/3. So we get pressure, and putting this all this value, we get the pressure P0 is to rho to the power 5/3. At finite temperature, the case is quite difficult, and we use some tricks to solve the equation. N equals to 2 pi n and E we got earlier, and we are writing these as using the previous calculations. We get a 3n by 2 epsilon f to the power 3/2, and this as 3n by 2 to epsilon to 3/2. The difference is that here the epsilon to the power half and epsilon to the power 3/2. Above integral is of the form I equals to 0 to infinity f epsilon t 5 epsilon d epsilon, where 5 epsilon equals to what? Epsilon to the power 3/2. It is a monotonic function of epsilon, and I equals to, monotonic means it will increase with epsilon, values of epsilon. I equals to f epsilon t psi epsilon, that is integration of 5 epsilon equals to psi epsilon. The psi epsilon and integration is 0 to infinity, and from the integration formula we can write that differentiation of the first, that is f prime epsilon t, the psi epsilon d epsilon. So first term vanishes because psi 0 equals to 0, and for f epsilon t at upper limit. Now I equals to minus sign f prime epsilon t psi epsilon d epsilon. So we can write psi epsilon equals to psi of epsilon f plus epsilon minus epsilon f into psi prime epsilon f plus half epsilon minus epsilon f whole square psi double prime epsilon f. Then I equals to, what we can write, what was that, f prime epsilon t into psi epsilon. So psi epsilon we expand like this and we get this. So the integration is psi epsilon f, this will come out because it is a constant value, and psi prime epsilon f is particular for a particular value of energy. This is a constant coming out, and f prime epsilon t, epsilon minus epsilon f prime epsilon t, and this 3 integration is to be done. I0 equals to I0 equals to minus infinity to plus infinity f prime epsilon t equals to 0 to infinity. We are as the function is not exist beyond the 0 value, so we can expand it arbitrarily minus infinity up to minus infinity. So total integration of a distribution function, total distribution function equals to 1, so integration comes out as 1. And the second I1, this is f prime epsilon d epsilon, the variation is like this. This is the even function, and this is the odd function epsilon minus epsilon. So the total integration is the even odd function, so it will increase in a total limit range of integration, it will be 0. And for I2 we can write epsilon epsilon whole square f prime epsilon d epsilon, and we write that epsilon minus epsilon whole square by kbt equals to x. We can write and change the variable like this, and the integration is a standard integration and comes out as pi square by 6 kbt whole square. At low temperature such that kbt is less than 0, the derivative f prime epsilon is large only at energy near epsilon f. So we get that the total integration I, so for all this, putting all this value, we can get the total integration I equals to psi epsilon f plus half, the second term was 0 and the last term is this. So we can write that psi epsilon equals to 0 to epsilon 5 epsilon d epsilon, from where we get 2/3 epsilon to the 3/2. The psi epsilon f equals to 2/3 epsilon f to the power 3/2. Psi prime epsilon f equals to epsilon to the power half, and psi double prime. Putting all this value, we get that I equals to 2/3 epsilon to the power 3/2, 1 plus pi square by kbt by epsilon whole square. Now n equals to, we have the previous slide, we get that n value of n equals to n into epsilon f by epsilon f 0 to the power 3/2, and this, and 1 equals to the n by n equals to 1, so 1 equals to this. So from this we get epsilon by epsilon 0 to the power 3/2, that is equals to epsilon f equals to epsilon f0 into 1 minus pi square by 8 kbt by epsilon f whole square to the power 2/3, that is equals to epsilon f0 1 minus pi square by 12 kbt by epsilon f whole square. With no much error, epsilon f is replaced by epsilon f0 in kbt by epsilon f. that if epsilon we are if we replace epsilon f by epsilon f 0, then there will be no much error. So we can write epsilon f equals to epsilon f 0 1 minus pi square by 12 kBT by epsilon f whole square. This is the relation, important relation, that how the epsilon f at any temperature can vary with temperature when the epsilon f at T equals to 0 Kelvin is known. This is the important relation we have to remember. And the total energy E equals to 3n by epsilon f 0 to the power 3 by 2 into the integration, putting the integration comes out at this. Here the epsilon f is, psi epsilon is different, and putting all these values we get 3n by 2 epsilon f to the 3 by 2, 2 by 5 epsilon f to the 5 by 2, 1 plus this. All these values are we get from the integration we have. And putting all these values here, we are putting the epsilon f by epsilon f, that is we got earlier in earlier slides, that epsilon by epsilon is 0, this epsilon f this, and to the power 3 by 2, and epsilon f we are putting this value here also, and 1 plus 5 pi square, right? And multiplying all these and taking only the first term is here is a whole square, kBT by epsilon f whole square. We are taking, multiplying and taking the first term, and we get these values at this 3 by 5 n epsilon 0 1 plus 5 pi square by 12 kBT by epsilon f whole square. So CV, what is CV? It is the change of energy with temperature and constant volume. We get the earlier from earlier integration E, and derivative with respect to T we get like this, and we see that it varies as epsilon CV of electronic specific heat varies as gamma T. That is all the are constant except T. So it varies with the constant, it varies with temperature, and gamma, the constant is comes out is like this, pi square n kb by 2 Tf. This is the electronic specific heat. Now we come to an application where the white dwarf star can be explained beautifully using the Fermi-Dirac distribution function. And what we get that here if a star is there are two forces coming, there are two forces in case of star. One is the gravitational attraction which transform the star, which contract the star, whereas the energy, thermal energy, that is the nuclear energy that is generated inside the star, which gives the energy to the star, and now the energies which comes out from the thermonuclear reaction. And the thermonuclear reaction, and when the star are losing energies, then what happens, the star are the balance between the two forces is not there, and that star tries to collapse. And in the collapsing, when in case of collapsing, actually when the star runs out of burnable fuel, it start to collapse. And it is basically a gas of electron and ion. As the star collapses, its density increases. Mean separation between the particle becomes of the order of de Broglie wavelength. And what happens that the ions, so electron, or here the electrons comes very near, and the de Broglie wavelength become a prominent thing. And we know from the Pauli exclusion principle that no two electron cannot be in a same state, so there will arise a pressure not to come in a compact state, and this pressure is degeneracy pressure, and this pressure prevent the collapse of the star, and then the star is called the white dwarf. And in calculation of this white dwarf star, when it will happen, you can get the total energy. We can write as total energy of the star like E equals to T plus U, time density energy plus potential energy, and the potential energy is the gravitational attraction energy and the gravitational energy, and this equals to minus 3 by 5 gm square by r, and where r is the stellar radius and m is the stellar mass. And we got earlier that Fermi momentum can be written as Fermi, from where we can get Fermi momentum, from the Fermi energy. We know that Fermi energy EF equals to Pf square by 2m, so Pf equals to C n by V whole to the power 1/3, where C equals to 3 pi square whole to the power 1/3 into H cross, and V equals to 4/3 pi r cube stellar volume, and equals to total number of electron contained in the star. Number of electron states contained in an annular radius of p space lying between the radius p and p plus dp is dn equals to 3v by cq. C is a constant. C is a constant. C equals to this. C is this constant, and so 4 pi p square dp into v. So we get the dn equals to 3v by cq p square dp. Total kinetic energy of the electron gas T equals to, where the p square by 2m into dn, that is equals to p square by 2m total kinetic energy into dn. So we get the value as 3 by 5n c square by 2m n by v to the power 2/3. The interior of a white dwarf star is composed of atom like carbon 12 and oxygen 16, which contain equal number of proton and neutron and electron. Thus we can write mass can be written as number of particles n, and the number of proton and neutron are same, so 2 into m into n. So E total energy can be written using all the previous thing. We can write 3 by 5n c square by 2m n by v to the power 2/3 minus 3 by 5 gm square by r. So we get that the variation of total energy, the this is varies as r square, and another one is varies as 1 by r. So E equals to a by r square minus b by r, where a equals to this and b equals to this. Equilibrium radius is obtained by d dr, that is derivative, and we get that r equivalent by r0 equals to 0.010 m0 by m to the power 1/3, r0 equals to 7 into 10⁵ kilometer. This is a stellar radius, and m0 2 into 10 to the 30 kg the solar mass. It follows the radius of a typical solar mass white dwarf is about, radius comes out as 7,000 kilometer, that is nearly equals to earth radius. Now the important thing here, the Chandrasekhar limit, the limit for a star to be a white dwarf. For a white dwarf, radius decreases as the mass increases. We got earlier that T varies as m to the power 5 by 3. Hence, for large mass, the electron become relativistic, and relativistic calculation needed. For simplicity, we consider the ultra relativistic case. That is, momentum is greater than mc. The total energy of electron can be written as total energy, kinetic energy T equals to 3v by cq. Integration from 0 to pf p square c square by m square c to the power 4 to the power half p square dp. That equals to taking the pc constant and 1 plus m square, and the first term taking only the first 1 plus x to the power n square 1 plus nx, we get the t equals to this 3 by 4 b.Sc by cq pf to the power 4 m square c square pf square. The total energy of an ultra relativistic white dwarf star can be written as equals to a minus b by r plus cr, where we get a minus b by r. It was the previously here the c, here c is the velocity of light, and this c, a capital C, is a constant we have defined earlier. So a equals to this, b equals to this, and c equals to this. From the equation we see that when a is less than b, when a is less than, energy decreases monotonically with decreasing stellar radius. The degeneracy pressure is unable to stop the collapse of the star. So we will not get the equilibrium when a is less than b. Let's say this is negative and this is the positive. When decreasing radius, it will decrease and it will also decrease. So there will be no equilibrium. To get the equilibrium value, a must be greater than equals to b. This gives the condition for non-zero value of r equilibrium radius. So the condition is a by b greater than 1. So putting the values of a and b, a is greater than b, and this we get mc greater than m. mc is a constant value of this. This is the value of mc. So the mass of the star, what we, the condition is mc greater than m, where mc equals to what? Is 15 by 16 5 pi s to the power half h cross c by g to the power 3 by 2 1 by m square equals to 1 plus 1.72 m0. This is the Chandrasekhar limit. So this is required to prevent the collapse. So a more accurate calculation considering the non-uniform density gives the result m equals to 1.4 m0. Thus, if the stellar mass exceeds the Chandrasekhar limit, then the star in the question that is the we are discussing in the theory that can become a white dwarf. Then the electron degenerate pressure cannot prevent gravitational collapse. When the density become very high, the star enter into new regime. For example, the star could explode into a supernova and collapse to form a very dense black dwarf. So this condition is important for formation of white dwarf. Thank you for your kind attention. Thank you.